Hello, in this lecture there are some two questions. The first question, we'll find out the area of this green shape by using two different methods. And in the second question, we find out the radius of this semicircle that is inscribed by this rectangle ABCD. So we start with the first question. In the drawing we have rectangle ABCD. This is line segment AE that equals to 1 unit in its length. Side AB of rectangle ABCD equals to 3 units in its length. Inside this rectangle we have this green shape. The green shape is actually the green rectangle ACEB. This angle equals to 45 degrees inside. Again, our test to find out the area of this green shape. This is actually the area of this green triangle CEB. Okay, so first of all, quadrilateral ABCD is a rectangle, so all those four angles are all rectangles. In the next step, we will define the length of this line segment ED is x. So AD in total equals to 1 plus x. We have the rule that says that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. But AB is 3, therefore the opposite side DC must be also equal to 3 units in its length. Likewise, according to the same rule, in the same rectangle ABCD, side AD must be equal to the opposite side BC. But AD is 1 plus x, therefore the opposite side BC must be also equal to 1 plus x units in its length. In the next step, we will focus on the upper right triangle, triangle ABE. We will implement the Pythagoras theorem on this upper right triangle, triangle ABE. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this right triangle ABE, here by PT is the abbreviation for Pythagoras theorem. This right triangle ABE, according to the Pythagoras theorem, BE squared, that is the square of the hypotenuse, equals to AB squared plus AE squared. Again, in this right triangle ABE, according to the Pythagoras theorem, BE squared, that is the square of the hypotenuse, equals to AB squared plus AE squared. BE is the missing hypotenuse, so we leave it as it is, so it is BE squared equals to AB squared. AB is 3, therefore AB squared is 3 squared, that is 9. Plus AE squared. AE is 1, therefore E squared is 1 squared, that is 1. So if you found out that BE squared equals to 9 plus 1, that is 10. BE squared equals to 10. Here we take out all those equations. If I get that BE, therefore the approach BE is equal to square root of 10 units. So this is the approach BE, or the other ABE, is equal to the square root of 10 units in its length. In the next step, we'll implement the Pythagoras theorem on this right triangle EDC. Again, we'll implement the Pythagoras theorem on this right lower triangle EDC. Here by PT is equation for Pythagoras theorem. In this lower right triangle EDC, E3 squared, that is the square of the hypotenuse, equals to the ED square plus DC square. And again, in this right lower triangle EDC, according to the Pythagoras theorem, EC squared, that is the square of the hypotenuse, equals to ED square plus DC square. EC is the base of the hypotenuse, so we'll leave it as it is. So it is EC square and it is equals to ED square. ED is x, therefore ED square is x square plus DC square. DC is 3, therefore DC square is 3 squared, that is 9. So in total, if you found out that EC square equals to x square plus 9. Here we take out all those equations. And finally we get that the hypotenuse EC, on the right hand EDC, is equal to the square root of x squared plus 9. This is the hypotenuse EC. This is equal to the square root of x squared plus 9. In the next step, we will do a construction. That is to say, from point E, we draw perpendicular on BC. Again, from point E, we draw perpendicular on side BC of this triangle EBC. So actually, this angle equals to 90 degrees inside, and this angle is also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point E and BC. Side BC, this point is point M. By doing this construction, we can do quadrilateral ABME. Side quadrilateral ABME, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total The sum of those four angles must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 pieces again must be equal to 9 degrees in its size. So in the quadrilateral ABME we have 4 degrees. Therefore we can relate to this quadrilateral is a rectangle. Writing on. So we have in the drawing 2 rectangles. This is the small rectangle ABEM. And also the big rectangle ABCD. In the small rectangle ABME, the sum of the angles are the sum. We know that the opposite sides of the rectangle are equal to each other. So in the small rectangle ABME, the opposite sides of the rectangle are equal to each other. That is to say, AB equals to the opposite side EM. But AB is 3, therefore the opposite side EM must be also equal to 3 units in its length. We define side EM as H, so EM equals to 3, therefore H equals to 3. H is the height to the base of grand triangle EBC. If the base is BC, then EM equals to H is the height to the base BC. Why? Because it is perpendicular to the base. Our task is to find out the area of this green shape. What is the green shape? The green shape is actually the green triangle EBC. So we have to find out the area of this green triangle EBC. So we calculate the area of this green triangle EBC in 2 different ways, and then here is an equation that says that the area of this green triangle EBC according to the first method of calculation must be equal to the area of the same green triangle EBC according to the second method of calculation. So in the first method of calculation, the area of this triangle EBC is equal to the base BC times the height ME, this is H, over 2. And again, the area of this green triangle EBC must be equal to the area of any triangle, that is the base of the triangle times the height over 2. So the area of this green triangle EBC according to the first method of calculation equals to the base BC times the height H over 2. So again, the area of this green triangle EBC according to the first method of calculation must be equal to the base BC times the height H over 2. We only found out that the base BC equals to x plus 1 units in its length times the height H. We only found out that the height H equals to 3 units in its length divided by 2. In total, we found out that the area of the green triangle BC according to the first method of calculation equals to x plus 1 times 3 over 2. So written down, the area of the green triangle BEC according to the first method of calculation equals to x plus 1 times 3 over 2. The next step, we calculate the area of this green triangle EBC in a different way. Okay. This is triangle ABC that could be any triangle. This triangle ABC, side AC equals to B units in its length. This is side AB, this is equals to A units in its length. The angle between those two sides is angle theta. The area of this triangle ABC equals to the multiplication of the two sides by each other, that is to say A times B times sinus theta over 2. And again, the area of this triangle ABC that could be any triangle equals to the multiplication of the two sides by each other, that is to say it is A times B times sinus theta over 2. Use the new formula in order to find out the area of our triangle BEC. The area of this triangle BEC is equal to side BE times side EC times sinus 45 degrees over 2. So it is known. So the area of this green triangle BEC according to the second method of calculation equals to BE times EC, that is the multiplication of those two sides by each other, times sinus the angle between the two sides, that is 45 degrees, over 2. So the area of this green triangle EBC according to the second method of calculation equals to the multiplication of the two sides by each other, that is to say BE times CC times sinus the angle between the two sides, that is sinus 45 degrees over 2. So in the next step we create the equation 3 that says that the area of this green triangle EBC according to the first method of calculation must be equal to the area of the same green triangle EBC according to the second method of calculation. The area of the green triangle EBC according to the first method of calculation must be equal to the area of the same green triangle EBC according to the second method of calculation. The area of the green triangle EBC according to the first method of calculation is equal to x plus 1 times 3 over 2. And it must be equal to the area of the same green triangle EBC according to the second method of calculation. The area of the right triangle EBC according to the second method of calculation equals to BE times EC times sinus 45 degrees over 2. And again, this is equation 3 that says that the area of the green triangle BEC must be, according to the first method of calculation, must be equal to the area of the same green triangle EBC according to the second method of calculation. So here we have 2 on both sides of this equation, so 2 will get cancelled. After we cancel 2, in this side of equation 3 we left only with x plus 1 times 3. And it is equal to, on the other side of the equation, we left with BE times EC times sinus 45 degrees. So in this side of equation 3 we have 3 times x plus 1. And on the other side of equation 3 we have BE times AC times sinus 45 degrees. We already found out that this is side BE, this is equal to the square root of 10 units in its length times EC. We already found out that side EC equals to the square root of x squared plus 9 units in its length. Times sinus 45 degrees. Sinus 45 degrees equals to the square root of 2 over 2. And again, so in total, according to the equation, we have found out that 3 times x plus 1 equals to BE is square root of 10, EC is square root of x squared plus 9, and sinus 45 degrees is square root of 2 over 2. So, square root of 2 times square root of 10 times square root of 2 is equals to the square root of 10 times 2, that is 20. Like the number, we found out that according to equation 3, three times x plus 1 equals to, again, the square root of 2 times the square root of 10 times the square root of 2 equals to the square root of 20 times x squared plus 9 over 2. So if you found out that according to equation 3, three times x plus 1 equals, we substitute 20 by 4 times 5, so inside the root we have 4 times 5 times x squared plus 9 times the square root of x squared plus 9 divided by 2. The square root of 4 is 2, so we take 4 out of the root, so inside the root we left only with square root of 5. So according to equation 3, we found out that 3 times x plus 1 equals the square root of 2, the square root of 4 is 2, so inside the root we left only with square root of 5 times square root of x squared plus 9 over 2. Here we have 2 in the numerator, 2 in the denominator, so 2 get cancelled. So in total we found out that 3 times x plus 1 equals to the square root of 5 times the square root of x squared plus 9. Here we square both sides of this equation, equation 3. And again that this side of equation 3 we have 3 squared is 9 times x plus 1 squared, and is equals to the square root of 5 squared equals to 5, and the square root of x squared plus 9 squared equals to x squared plus 9. Well, because the square cancels the root and we left only with x squared plus 9. So total, actually found out that 9 times x plus 1 squared equals to 5 times x squared plus 9. Here we will open the brackets on both sides of this equation, equation 3, and again that according to equation 3, inside we have 9 times x squared, x plus 1 squared. X plus 1 squared equals to x squared plus 1 squared, that is 9, plus 2 times x times 1, that is 2x, and it equals to 5 times x squared equals to 5x squared, plus 5 times 9 is 45. Here we'll open the brackets on this side of this equation, equation 3, and we get that 9 times x squared is 9x squared, plus 9 times 1 is 9, plus 9 times 2x is 18x, equals to 5x squared plus 45. Here we will subtract 5x squared from this equation, equation 3, and get that 9x squared minus 5x squared equals to 4x squared plus 18x plus 9 equals to 45. Here we subtract 45 from this equation, equation 3, and find out that according to equation 3, on the side of equation 3 we have 4x squared plus 18x, and 9 minus 45 is minus 36, equals to 0. Okay, again, found out according to equation 3, 4x squared plus 18x minus 46 equals to 0. Here we will divide this equation, equation 3, by 4. And get that according to this equation, equation 3, 4x squared over 4 is x squared, plus 18x over 4 is 4.5x, and minus 36 over 4 is minus 9, equals to 0 over 4 is 0. So in total, we should find out that according to equation 3, x squared plus 4.5x minus 9 equals to 0. So this is a quadratic equation. And the general formula for a quadratic equation is as follows: ax squared plus bx plus c equals to 0. This general formula, a, b, and c are the coefficients of this quadratic equation. And x is the variable that we are looking for. We find out the value of x according to the following formula: x equals to minus b plus minus square root of b squared plus 4 times a times c over 2a. Now a specific quadratic equation, that is to say x squared plus 4.5 x minus 9 equals to 0. The variable that we are looking for is x. The coefficient a equals to 1. The coefficient b equals to 4.5. And finally the coefficient c equals to minus 9. So the only thing that is left to do in order to find out the value of x, that is the variable that we are looking for in our specific quadratic equation, is just to put the data of our specific quadratic equation inside this general formula for x. In this way we find out the value of the values of x, because x might have two solutions. We'll do it now and get that x equals to minus b. B is 4.5, and therefore minus b is minus 4.5 plus minus square root of b squared. B is minus 4.5. Actually, b is 4.5. Again, x equals to minus b, so b is 4.5, therefore minus b is minus 4.5. Plus minus square root of b squared. B is 4.5, therefore b squared is 4.5 squared, that is 20.25 minus 4 times a times c. So it is minus 4 times a is also minus 4 times 1 is minus 4 times c. C is minus 9, and therefore minus 4 times minus 9 is plus 36. So inside the root we have 20.25 plus 36 divided by 2a. A is 1, so 2a is 2 times 1, that is 2. So do that, we found out that x equals to minus 4.5 plus minus, inside the root we have 20.25 plus 36, that is 56.25 divided by 2. So x equals to minus 4.5 plus minus, and the square root of 56.25 is 7.5 divided by 2. But again, in total, we should find out that x equals to minus 4.5 plus minus 7.5 divided by 2. So here we will have two solutions that are possible for x. The first solution for x is as follows. X equals to minus 4.5 minus 7.5 over 2. Minus 4.5 minus 7.5 is minus 12 over 2. Minus 12 over 2 is minus 6. So the first solution for x is that x equals to minus 6. X equals to minus 6. But because of the fact that x is the left of right side ED, so x as a length, it must be a positive number. Minus 6 is a negative number, therefore x can never be equal to minus 6, that is a negative number. X must be a positive number. So we can say the first solution for x, and we'll take into account only the second solution for x. The second solution for x is as follows. X equals to minus 4.5 plus 7.5 over 2. Minus 4.5 plus 7.5 is 3 over 2. 3 over 2 is 1.5. So today we found out that x equals to 1.5 units in its length. This is 970 ED equals to x, and x equals to 1.5 units in its length. Our task is to find out the area of this green shape. What is the green shape? The green shape is actually the green triangle EBC. Is again the green shape is actually the green triangle BCE. The green triangle EBC. Our task is to find out the area of the green triangle EBC. What is the area of this green triangle EBC? The area of this green triangle EBC equals to the base of the triangle that is BC times the height that is h divided by 2. And again, the area of the green shape, it is actually the area of the green triangle EBC. The area of the green triangle EBC equals to the base BC times the height h over 2. BC equals to 1 plus x times the height edge over 2. So the area of the green shape in total equals to 1 plus x. X is 1.5, so 1.5 plus 1 is 2.5. So BC in total, the base BC equals to 2.5 units in its length times the height edge. We only found out that the height edge equals to 3 units in its length. So edge is 3 over 2. So the area of the green shape in total equals to 2.5 times 3 is 7.5 over 2. 7.5 over 2 equals to 3.75 square units in size. So if you found out that the area of the green shape, that is the area that you're looking for, in total it is equals to 3.75 square units in size. So we finish with the first method. In the next step I present to you how to find out the area of this green shape according to the second method. ABCD is a rectangle, therefore all those four angles are all right angles. This is a right angle. This is also a right angle. This is a right angle. And this is also a right angle. When you find the length of this line side ED is x, exactly as we did in the first method, the total AD equals to 1 plus x. We also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. But AB is 3, therefore the opposite side DC must be also equal to 4 units in its length. Likewise, according to the sum rule, in the sum rectangle ABCD, side AD must be equal to the opposite side BC. But AD in total equals to x plus 1, therefore the opposite side BC must be also equal to x plus 1 units in its length. In the next step, we will do a construction, exactly as we did in the first method. That is to say, from point D, we will do a perpendicular on side BC. Again, from point D, we will do a perpendicular on BC. So okay, this angle equals to 90 degrees inside, and this angle also equals to 90 degrees inside according to our construction. We define the touching point of the perpendicular from point A and BC. This point is point M. When doing this construction, we can do the small quadrilateral ABME. Inside the small quadrilateral ABME, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle in total must be equal to 360 degrees. According to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in size. So inside quadrilateral ABME we have right angles, and the four connected to this quadrilateral ABME is right angle. We define the perpendicular from point E to BC. This perpendicular EM SH. This is the relation for height. That is to say EM equals to adjacent left according to our definition. We know that the opposite sides of a rectangle are equal to each other. So in rectangle ABME, side AB must be equal to the opposite side EM. But AB equals to 3, therefore the opposite side EM must be also equal to 3 and it's in itself. But EM equals to H and H equals to 3. Therefore H equals to 3. That is to say, the height to the base BC, H equals to 3 and it's in its length. So all the things that are already done in the second method, we already done in the first method. Now in the second method, we will do another thing. That is to say, we will define this angle AEB as theta. And we will focus on the upper right triangle, triangle ABE. This is the upper right triangle, triangle ABE. This upper right triangle, triangle ABE, tangent theta equals to AB over AE. Okay, again, this right triangle, triangle ABE. Tangent theta equals to AB over AE. AB is 3, AE is 1. So if you found out that tangent theta equals to 3 over 1, that is 3. So according to equation 1, we actually found out that tangent theta equals to 3. We have the trigonometric identity that states that tangent theta plus 45 degrees equals to 1 plus tangent theta over 1 minus tangent theta. This will be equation 2. We already found out that tangent theta equals to 3. Therefore, we can substitute tangent theta in this trigonometric identity by 3. We do it now and get that tangent theta plus 45 degrees equals to 1 plus tangent theta. It is 1 plus tangent theta. Tangent theta is 3 over 1 minus tangent theta. Again, tangent theta is 3. So total tangent theta plus 45 degrees equals to 1 plus 3, that is 4, over minus 3, that is minus 2. Minus 4 over minus 2 is minus 2. So total according to equation 2, we actually found out that tangent theta plus 45 degrees equals to minus 2. This is according to equation 2. AD is one side of rectangle ABCD, and therefore it is absolutely a straight line. AD is the side of a rectangle, it is absolutely a straight line. So if you focus on the right side of the straight line AD at point E, here the sum of the angles must be equal to 180 degrees according to all three. All three says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of the straight line AD at point E? We have this angle that is theta plus 45 degrees plus this third missing angle. In total must be equal to 180 degrees according to all three. So it is known. According to all three, the sum of the angles on the right side of the straight line AD at point E must be equal to 180 degrees. That is to say theta plus 45 degrees plus the missing angle that is actually angle EDC. This is angle DEC. Angle DEC. This is the missing angle. Total must be equal to 180 degrees according to all three. So again, the sum of the angles on the right side of the straight line AD at point E must be equal to 180 degrees. That is to say theta plus 45 degrees plus the missing angle DEC in total must be equal to 180 degrees according to all three. So here we subtract theta plus 45 degrees from this equation and find out that the missing angle DEC equals to 180 degrees minus theta plus 45 degrees. This is the missing angle DEC, that equals in total to 180 degrees minus theta plus 45 degrees. In the next step, we will focus on this right lower triangle, triangle EDC. In the right lower triangle, triangle EDC, tangents 180 degrees minus theta plus 45 degrees equals to DC over AD. So it is known. The entire EDC tangents of this angle is occurring angle 180 degrees minus theta plus 45 degrees equals to DC over AD. But again, in this right triangle EDC, tangents theta, tangents of 180 degrees minus theta plus 45 degrees equals to DC over AD. DC is 3 over AD, AD is X. So in total, we found out that tangents 180 degrees minus theta plus 45 degrees equals to 3 over X. This is equation 3. And again, we should found out that according to equation 3, tangents 180 degrees minus theta plus 45 degrees equals to 3 over X. So according to equation 3, we have another trigonometric identity that states that tangents 180 degrees minus theta equals to minus tangent theta. So according to this trigonometric identity, tangents 180 degrees minus theta plus 45 degrees will be equal to minus tangent theta plus 45 degrees. This is minus tangent theta plus 45 degrees. And again, according to this trigonometric identity, tangents 180 degrees minus theta equals to minus tangent theta. We get that the value of tangents 180 degrees minus theta plus 45 degrees equals to minus tangents theta plus 45 degrees. And it is equals to 3 over x. This is according to equation 3. But according to equation 2, we already found out that tangent theta plus 45 degrees equals to minus 2. So we substitute tangent theta plus 45 degrees in equation 3 by minus 2. So in this equation 3, in total we have minus, and tangent theta plus 45 degrees according to equation 2 equals to minus 2. So we have minus 2 equals to 3 over x. Minus times minus is plus, so minus 2 is plus 2. So according to equation 3, we found out that two equals to 3 over x. Here we multiply this equation 3 by x. When you get that according to equation 3, 2x equals to 3. Here we divide this equation 3 by 2, and find that x equals to 3 halves. 3 halves is 1.5. So if you found out that x equals to 1.5, and it's in its name. This is 970 ED is equals to x, and x is equals to 1.5 units in its name. Our task is to find out the area of this green shape. The green shape is actually the green triangle EBC. So our task is to find out the area of this green triangle EBC. And again, our task is to find out the area of the green shape, but the green shape is actually the green triangle EBC. So our task is to find out the area of the green triangle EBC. The area of any triangle equals to the base of the triangle times the height over 2. So we choose the base of this triangle BC as BC. So it is the base BC times the height edge over 2. So the area of the green shape equals to the base BC times the height edge over 2. BC is x plus 1, the base BC equals to x plus 1, times the height edge is 3 over 2. So total we found out that the area that we're looking for this question, that is the area of the green shape, equals to x plus 1 times 3 over 2. X is 1.5. So we found out that x equals to 1.5 units in itself. Therefore x plus 1 is 1.5 plus 1, that is 2.5 times 3 over 2. 2.5 times 3 is 7.5. So this is 7.5 over 2. 7.5 over 2 is 3.75 square inches inside. So that we found out that the area that we're looking for in this question, that is the area of the green shape, in both methods is equal to 3.75 square units in size. Okay, again, in both methods, we should find out that the area of this ring shape, that is the area that we are looking for in this question, is equal to 3.75 square units in size. So we finish with the first question. The next step I present to the second question, and we'll solve the second question of this lecture. In the second question, our task is to find out the radius of this semicircle. So in the drawing, we have rectangle ABCD. Inside rectangle ABCD, we have this semicircle. You can say that the semicircle is inscribed by rectangle ABCD. We also know that this is the small line segment cubic, is equal to 1 unit in center. This is line segment PD, it is equal to 2 units in center. And again, ABCD is a rectangle. And our task is to find out the radius of this semicircle. Okay. ABCD is a rectangle, therefore all those four areas are right angles. In the next step, we define the center of this semicircle. This point is point O, and we define the radius of this semicircle as x. Therefore, line segment OP is the radius of this semicircle. It equals to x according to our definition. Likewise, line segment OQ is also the radius of this semicircle, therefore it is equals to x according to our definition. In the next step, we define the point of tendency of tangent DC with this semicircle. This point is point L. Likewise, we define the point of tendency of tangent BC with this semicircle. This point is point T. And we will join points O and L together by straight line. Point O is the center of the semicircle, point L is the point of the semicircle itself, therefore OL is the radius of the semicircle, that equals to x. Here we can implement rule 1. Why? Because the radius OL z equals to x, the radius OL is drawn to point L, that is the point of tendency of tangent DC with this semicircle. Whenever your radius is drawn to the point of tendency, then tangent DC will be perpendicular to the radius LO. If DC is perpendicular to LO, it means that this angle equals to 90 degrees in its size. This angle also equals to 90 degrees according to rule 1. Likewise, we join points O and T together by side line. Okay, again, we join points O and T together by side line. Point T is the point of tendency of tangent BC with this semicircle. OT is, of course, the radius of this semicircle, equals to x. The radius OT equals to x. The radius OT is equals to x. The radius OT is drawn to point T, that is the point of tendency of tangent BC with this semicircle. Whenever your radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius TO. If BC is perpendicular to TO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to the sum rule, rule 1. So, in quadrilateral OLCT, we have 1, 2, 3 angles. The sum of 3 angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle in total must be equal to 360 degrees, according to the rule that said that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in size. So quadrilateral OLCT is 4 angles, therefore can relate to quadrilateral OLCT is a rectangle. But you also know that the opposite sides of rectangle are equal to each other. So the small rectangle OTCL, side OT must be equal to the opposite side LC, but OT is x, therefore the opposite side LC must be also equal to x units in its length. Likewise, according to the sum rule, in the same small rectangle OTLC, side OL must be equal to the opposite side TC, but OL is x, therefore the opposite side TC must be also equal to x units in its length. So she found that the small quadrilateral OTCL is not a rectangle but a square. Why? Because all of its sides are equal to each other, its side equals to x. So the small quadrilateral OTCL is a square. In the next step, we will do a construction, that is to say from point O, that is the center of this semicircle, we will do perpendicular on AB. Again, from point O, we will do perpendicular on side AB of this rectangle ABCD. So actually, this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size according to our construction. We will define the touching point of the perpendicular from point O and AB. This point is point Z. By doing this construction, we can deduce the small upper quadrilateral ZPTO. Inside this quadrilateral ZPTO, we have 1, 2, 3 angles, and therefore this fourth missing must be equal to 90 degrees in size. According to the sum rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. The quadrilateral ZPTO is 4 angles, and therefore can relate to quadrilateral ZPTO as a rectangle. So this is the upper small quadrilateral ZPTO. This is a rectangle because it has 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle ZPTO, side OT must be equal to the opposite side ZB. But OT is X, therefore the opposite side ZB must be also equal to X units in its length. What is the length of this line segment? Line segment ZQ. ZQ in total equals to ZB minus QB. Again, ZB minus QB equals to ZQ. So now the missing line segment ZQ equals to ZB minus QB. So in total, the short line segment the missing line segment ZQ equals to ZB. ZB is X. Minus QB. QB is 1 according to what is given in the question. So in total we found out that this is the missing line segment ZQ. This is equal to X minus 1 units in its length. In the next step we will do another construction, that is to say from point O, that is the center of this semicircle, we will draw perpendicular on AD. Again, from point O, we will draw perpendicular on side AD of this rectangle, rectangle ABCD. So here, this angle equals to 90 degrees in size, and this angle also equals to 90 degrees in size according to our construction. We define the touching point of the perpendicular from point O and AD. This point is point K. Quadrilateral, by doing this construction, we get the small quadrilateral AZ OK. Inside this small quadrilateral AZ OK, we have 2 free rectangles, and therefore this fourth missing angle must be equal to 90 degrees in size according to the rule that says that the sum of the angles in any quadrilateral is equal to 180 degrees. So quadrilateral AZOT is 4 rectangles, and therefore can relate to quadrilateral AZOT is a rectangle. By doing this construction, we can get another quadrilateral. This is quadrilateral OKDL. Inside quadrilateral OKDL, we have 1, 2, 3 rectangles. This is a right angle according to rule 1. This is a right angle according to our construction. And this is a right angle because ABCD is a right angle. So in total, in quadrilateral OKDL, we have 3 right angles, and therefore this fourth missing angle must be equal to 90 degrees in size. So inside quadrilateral OKDL, we have 4 rectangles, and therefore can relate to this quadrilateral OKDL as a rectangle. But you also know that the opposite sides of a rectangle are equal to each other. So in rectangle OKDL, side OL must be equal to the opposite side KD. But OL is X, and therefore the opposite side KD must be also equal to X units in its length. What is the length of this missing line segment? Line segment KP. From the drawing, it is very easy to see that Kp in total equals to Kd minus Pd. Again, Kd minus Pd equals to Kp. So, right now, the missing line segment Kp equals to Kd minus Pd. So, Kp in total equals to Kd is X. Minus PD. PD is 2 according to what is given as the question. So in total, we found out that the missing line segment Kp equals to X minus 2 units in its length. This is angle KOT. The size of angle KOT equals to 90 degrees plus 90 degrees is 180 degrees. So it is now this is angle KOT is equals to 180 degrees in size. But we know that any angle is equal to 180 degrees in size, it is defined as a straight line. This angle KOT is equal to 180 degrees in size, and therefore line segment KOT is a straight line. Again, this is line segment KOT, this is a straight line. Line segment KOT is a straight line. So if line segment KOT is a straight line, then KT is also a straight line. And then KT is a straight line. KT is a straight line. So this is shape TK AB. Again, this is shape TK AB. Shape TK AB. This is shape TK AB. Shape TK AB is 1, 2, 3, 4 sides. Shape TKAB is 4 sides. Therefore, shape ABTK is a quadrilateral. So it has 4 sides. Shape TKAB is a quadrilateral. So this is quadrilateral ABTK. In quadrilateral ABTK we have 1, 2, 3, 4 right angles. And we know that any quadrilateral that has 4 right angles must be this rectangle, if not a square. So we relate to quadrilateral ABTK is a rectangle. Quadrilateral TKAB is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are parallel to each other. So in rectangle ABTK, side AB must be parallel to the opposite side TK. And the non-AB is parallel to TK. According to the rule that the opposite sides of a rectangle are parallel to each other. So here we can implement rule 10 in our drawing. I'm going to quickly on rule 10. According to rule 10, corresponding angles between parallel lines are equal to each other. In the drawing we have line A, this is parallel to line B. This is line C, this is the transversal line. So line C, the transversal line, cuts the two parallels A and B. Those 2 points. Those 2 angles are both defined as corresponding angles and they are located between the parallels A and B, therefore they are equal to each other in their sizes. You can see those 2 angles are both equal to 1, therefore they are equal to each other in their sizes. Likewise, those 2 angles are also defined as corresponding angles, and because of the fact that those 2 corresponding angles are located between the parallels A and B, they must be equal to each other in their sizes. are equal to each other, and the sizes because both of them are equal to 2. So according to this rule 10, corresponding angles between the parallel lines are equal to each other. So we can actually implement rule 10 in our drawing. When put in our drawing, those two angles are defined as corresponding angles, and they are located between the parallels AB and KT. Again, AB is parallel to TK. And again, those two corresponding angles are located between the parallels AB and TK. And therefore, according to rule 2, they are equal to each other in their sizes. Okay. According to rule 10, the corresponding angles between parallels are equal to each other. Those two corresponding angles are located between the parallels AB and TK, therefore they are equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to rule 10. So in this upper right triangle OZQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, this is the lower right triangle KOP. The lower right triangle KOP. This angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha, according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we will prove that the green, this is the green right triangle OQZ, that this green right triangle OQZ can point to this right lower triangle KPO. So we will prove that those two green right triangles can point to each other according to angle side angle rule. So it is now, we have to prove that this is the green right triangle ZQO. And it is congruent to this green right triangle KPO. So why those two right green triangles can go into each other? First of all, those two angles are both equal to alpha, and therefore they are equal to each other. This is angle ZBO. In the right upper triangle ZBO, and it equals to this angle, this is angle KOP. The green right lower triangle KOP. And again, we should find out that the green upper right triangle ZBO, angle ZBO in the green upper right triangle ZBO is equal to angle KOP in the right lower green triangle KPO. They are both equal to alpha, and therefore they are equal to each other. In addition, side QO of this green upper triangle equals to side OP of this green lower triangle. They are both the radii of the semicircle, and therefore they are equal to each other. So it is known. This is side QO of the green right triangle ZQO. and it is equal to this side, that is side OP, of the right lower triangle KOP. Repeat again, side QO of the upper green triangle ZQO is equal to side OP of the right green lower triangle KPO. The above the radii of the semicircle is equal to X, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So actually, this is angle ZOQ in the right upper green triangle ZQO, and this is equal to this angle. This is actually angle OPK in the right green lower triangle KPO. Okay, again, I should find out that angle ZQO in the upper right green triangle ZQO is equal to angle KPO in the right lower green triangle KPO. They are both equal to 90 degrees minus alpha, and therefore they are equal to each other. And therefore those two right green triangles can go into each other according to angle side angle rule. So it is done. And I should find out that the upper right green triangle ZQO congruent, this is the sign of congruent, to the right lower green triangle KPO according to angle side angle rule. That is to say, I have found out that those two angles and the side that is included between those two angles, that is side QO and this upper green triangle ZQO, are corresponding equal to those two angles, and the side that is included between those two angles, that is side OP, this right lower green triangle KOP. Therefore, those two right green triangles can go into each other according to angle side angle rule. We have those two angles and the side that is included between those two angles in this upper green triangle are corresponding equal to those two angles, and the side that is included between those two angles in this right lower triangle KOP. Therefore, those two right triangles can go into each other according to angle side angle rule. And from the fact that those two right triangles can go into each other, we will derive that their corresponding sides must be also equal to each other in their lengths. According to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore their corresponding sides must be also equal to each other in their lengths. This is side ZQ. The corresponding side of side ZQ is side KO. Why ZQ is the corresponding side of side KO? Because of the fact that those two sides are both located in front of this angle that is 90 degrees minus alpha, and therefore the corresponding sides. So she found out that according to the rule that says that corresponding sides in congruent triangles are equal to each other, we know that side ZQ is equal to the corresponding side KO. But we already found out that ZQ equals to X minus 1. So we can write here that ZQ equals to X minus 1. And from this equation, X minus 1 equals to ZQ equals to KO. We know that the missing side KO must be equal to X minus 1 units in itself. This is the missing side KO is equal to X minus 1 units in itself. In the next step, we will implement the quadratic theorem on this right green triangle, KPO. Here by PT is evaluation for Pythagoras theorem. In this given triangle KPO, according to the Pythagoras theorem, all p squared, that is the square of the hypotenuse, equals to KO squared plus KP squared. And again, in this can I triangle KPO, according to the Pythagoras theorem, all p squared, that is the square of the hypotenuse, equals to KO squared plus KP squared. OP is x, therefore OP squared is x squared. And it is equals to KO squared. KO is x minus 1, therefore KO squared is x minus 1 squared. Plus KP squared. KP is x minus 2, therefore KP squared is x minus 2 squared. So in total we should found out that x squared equals to x minus 1 squared plus x minus 2 squared. Here we will open the brackets on this side of this equation and get that x squared equals to x minus 1 squared. X minus 1 squared equals to x squared plus 1 squared, that is 1, minus 2 times x times 1, that is minus 2x, plus x minus 2 squared. X minus 2 squared equals to x squared plus 2 squared, that is 4, minus 2 times x times 2, that is minus 4x. So here we have x squared on both sides of this equation, so x squared will get cancelled. After we cancelled x squared, in the side of the equation we left with nothing, that is to say 0. And on the other side of the equation we have 1 plus 4 is 5. Minus 2x minus 4x is minus 6x. Plus x squared equals to 0. So in total we have found out the 0 equals to 5 minus 6 squared plus x squared, or x squared minus 6x plus 5 equals to 0. This is a quadratic equation, and the general formula for a quadratic equation is as follows: ax squared plus bx plus c equals to 0. This is the general formula. A, b, and c are the coefficients of this quadratic equation. And x is the variable that we are looking for. And we'll find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say x squared minus 6x plus 5 equals to 0, the variable that we are looking for is x. The coefficient a equals to 1, the coefficient b equals to minus 6, and the coefficient c equals to 5. So we have all the data that is needed in order to find out the variable that we are looking for. That's x. X is the radius of the semicircle. You just have to put the data of our specific quadratic equation inside this general formula for x, and this way we find out the value of the values of x, because x might have two solutions. So we do it now, you get that the variable that we are looking for is x, that is the radius of the semicircle, equals to minus b. B is minus 6, so therefore minus b is minus 6, that is plus 6, plus minus square root of b squared. B is minus 6, therefore b squared is minus 6 squared, that is 36, minus 4 times a times c. A is 1, so minus 4 times 1 is minus 4 times c. C is 5, so minus 4 times 5 is minus 20. So total minus 4 times a times c is minus 20. So inside the root we have in total 36 minus 20 over 2a. A is 1, so 2a is 2 times 1, that is 2. So if we found out that x equals to 6 plus minus, inside the root we have 36 minus 20 is 16. So inside the root we have to leave 16 over 2. So x equals to 6 plus minus, the square root of 16 is 4 over 2. So we should find out in total that x equals to 6 plus minus 4 over 2. See again, we should find out that x equals to 6 plus minus 4 over 2. So here we will have two solutions that are possible for x. That is the radius of the semicircle. That is the radius that we are looking for in this question. The first solution for x is that x equals to 6 plus 4 over 2. 6 plus 4 is 10, and 10 over 2 is 5. So the first solution for x, let's say the radius x of the semicircle is equal to 5 units in its length. We have another solution for x. The second solution for x is as follows. X equals to 6 minus 4 over 2. 6 minus 4 is 2, and 2 over 2 is 1. So the second solution for x is that x equals to 1 unit in its length. But x can never be equal to 1 because line segment KP equals to x minus 2. According to what we already found out, line segment KP equals to x minus 2 units in its length. If x equals to 1, then Kp equals to x minus 2, that is, to say it is 1 minus 2, that is minus 1. If you found out that the length of line segment Kp is a negative, but Kp is a length, and as a length it must be a positive number. Kp as a length can never be equal to a negative number. Therefore, x equals to 1 is equal to a solution. Another reason that x can never be equal to 1 because of the fact that, again, Kp equals to x minus 2. Again, Kp is the length. As a length, it must be a positive number. That is to say, it must be greater than 0. So we have an equality that says that x minus 2 must be greater than 0. Here we will add 2 to this inequality and finally get that x must be greater than 2. If x must be greater than 2, x can never be equal to 1, that is less than 2. So we have two reasons that x can never be equal to 1. So we consider the solution and we left only with the other solution for x, that is actually x equals to 5 units in its length. So the radius of the semicircle equals to 5 units in its length. And again, the radius of this semicircle, x equals to 5 units in its length. So we finished to answer the second question. In the next step, I'll summarize the lecture. We start with the repetition of the first question and then repeat on the solution of this second question. Our task in the first question is to find out the area of this ring shape. So in the drawing we have a rectangle ABCD. This is line segment AE, this is equals to 1 unit in its length. Side AB of rectangle ABCD equals to 3 units in its length. Inside this rectangle ABCD we have this green shape. The green shape is actually the green tile EBC. This is again BEC, this is equals to 45 units in its size. Again, our task is to find out the area of this green shape, that is actually the area of the green tile BEC. Okay, so we start with the repetition of the first method. Repeat on the solution according to the first method. First of all, quadrilateral ABCD is a rectangle, and therefore all those 4 angles are right angles. We define the length of this line segment AED as x. So total AED equals to 1 plus x units in its length. We also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. But AB is 3, therefore the opposite side DC must be also equal to 4 units in its length. Likewise, according to the same rule, in the same rectangle ABCD, side AD must be equal to the opposite side BC. But AD in total is 1 plus x, and therefore the opposite side BC must be also equal to 1 plus x units in its length. In the next step, we did the construction, that is to say, from this point E, we do perpendicular on BC. Again, from point E, we do perpendicular on side BC. Of this rectangle ABCD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point E and BC. This point is point M. By doing this construction, we can delete quadrilateral AB and ME. Inside quadrilateral AB and ME, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the size of this 4th missing angle. In total, they must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4th missing angle must be equal to 9 degrees in its size. So inside quadrilateral AB and ME, we have 4 rectangles, and therefore we can relate to quadrilateral AB and ME is a rectangle. And you also know that the opposite sides of the rectangle are equal to each other. So in the small rectangle AB and ME, side AB must be equal to the opposite side EM. But AB is 3, therefore the opposite side EM must be also equal to 3 units in its length. EM is perpendicular to BC, so we define the length of EM as h. It is a version for height because it is the height to the base BC of the rectangle BEC. So we define the length of EM as h. So EM equals to 3, therefore EM equals to h equals to 3 units in itself. That is to say, h equals to 3 units in itself. That is to say, the height to the base BC of the rectangle BEC equals to 3 units. H equals to 3. In the next step, we focus on this upper right angle triangle AEB. Implemented the Pythagoras theorem on this right upper triangle triangle AEB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this right triangle AEB, BE squared, that is the square of the hypotenuse, equals to AE squared plus AB squared. And again, this right upper triangle AEB, according to the Pythagoras theorem, BE squared, that is the square of the hypotenuse, equals to AB squared plus AE squared. BE is the missing hypotenuse, so so it is BE squared equals to AB squared. AB is 3, therefore B squared is 3 squared, that is 9, plus AE squared. A is 1, so A squared is 1 squared, that is 1. So we should find out that BE squared equals to 9 plus 1, that is 10. So BE squared equals to 10. Here we took out all the equation and found out that the missing hypotenuse BE equals to the square root of 10 units in its length. This is the hypotenuse BE, this is equals to the square root of 10 units in its length. Likewise, implement the Pythagoras theorem on this right lower triangle, triangle EDC. According to the Pythagoras theorem, in this right lower triangle, triangle EDC, EC squared, that is the square of the hypotenuse, equals to ED squared plus DC squared. And again, this right lower triangle, triangle EDC, EC squared, that is the square of the hypotenuse, equals to ED squared plus DC squared. EC is the missing hypotenuse, so when it is so it is EC squared equals to ED squared. ED is x, therefore ED squared is x squared plus DC squared. DC is 3, therefore DC squared is 3 squared, that is 9. So in total we found out that EC squared equals to EC squared equals to x squared plus 9. Here we took out all of this equation and found out that the missing hypotenuse EC equals to the square root of x squared plus 9 units in its length. This is the hypotenuse EC, is equals to the square root of x squared plus 9 units in its length. In the next step, we calculated the area of this green triangle ABC, that is actually the area of the green shape, that is the area that we're looking for in this equation, in two different ways. And then we get an equation that says that the area of triangle BC according to the first method of calculation must be equal to the area of the same triangle BC according to the second method of calculation. So in the first method of calculation, the area of this triangle ABC equals to the base BC times the height edge over 2. This is equation 1. So according to the first method of calculation, the area of the green triangle ABC, that is the area of the green shape, that is the area that we're looking for this equation, equals to the base BC times the height edge over 2. BC is x plus 1, edge is 3 over 2. BC is x plus 1, edge is 3 over 2. So in total we found out that the area of the green triangle BC, that is the area that we're looking for, that is the area of the green shape, equals to x plus 1 times 3 over 2. In the next step, we calculated the area of this green triangle ABC according to the second method. Actually, we have a special formula for the area of any triangle. This is triangle ABC that could be any triangle. Side AC of this triangle ABC equals to B units in itself. This is side AB, equals to A units in itself. And the angle between A and B is theta. So the area of this triangle ABC that would be any triangle equals to the multiplication of the two sides by each other times sine of the angle between the two sides, it is theta over 2. But again, according to the second method of calculation, the area of this triangle ABC that would be any triangle equals to A times B times sine of theta over 2. So we can implement the new formula in order to find out the area of this triangle BC, because the area of triangle BC that represented to could be any triangle. So the area of the green triangle BC equals to the multiplication of the two sides by each other, that is to say it is BE times CC times sine of the angle between the two sides, that is 45 degrees over 2. So in total, the area of this green triangle BEC according to the second method of calculation equals to BE times EC times sine of 45 degrees over 2. So according to the second method of calculation, the area of the green triangle BC equals to the multiplication of two sides by each other, that is to say BE times EC times sine of the angle between the two sides, that is 45 degrees over 2. The next step, we created the equation 3 that said that the area of triangle ABC according to the area of the triangle ABC according to the first method of calculation must be equal to the area of triangle ABC according to the second method of calculation. The area of the triangle ABC according to the first method of calculation equals to x plus 1 times 3 over 2, and it must be equal to the area of the triangle ABC according to the second method of calculation. Area of the triangle ABC according to the second method of calculation equals to BE times AC times sinus 45 degrees over 2. So this is equation 3. We have 2 on both sides of this equation 3, so 2 will get cancelled, then we cancel 2, and this side of the equation we left only x plus 1 times 3, while on the other side of the equation we left only BE times EC times sinus 45 degrees. So we have x plus 1 times 3 equals to BE is square root of 10 times EC is square root of x squared plus 9 times sinus 45 degrees, that is square root of 2 over 2. So here we have square root of 10 times square root of 2 is square root of 20, and we also square root of x squared plus 9 over 2. Twenty is 4 times 5, so we substitute 20 by 4 times 5. So inside the root we have 4 times 5, so in total we should find out that 3 times x plus 1 equals to the square root of 4 times 5 times x times the square root of x squared plus 9 over 2. The square root of 4 is 2, so we took 4 out of the root, so inside the root we left only with 5. So in total the area of we found out that 3 times x plus 1 equals to, again, the square root of 4 is 2. So the root we left only with 5 times the square root of x squared plus 9 divided by 2. We have 2 in the denominator, so 2 will get cancelled, so cancel 2. We found out that 3 times x plus 1 equals to the square root of 5 times the square root of x squared plus 9. Here we scored both sides of this equation, equation 3. So 3 squared is 9 times x plus 1 squared equals to the square root of 5 squared is 5, and the square root of x squared plus 9 squared equals to x squared plus 9. Why? Because of the fact that the square cancels the root, and we left only with x squared plus 9. So total we found out that 9 times x plus 1 squared equals to 5 times x squared plus 9. Here we open the brackets on both sides of this equation, equation 3, and found out that according to this equation, equation 3, 9 times x squared, 9 times x squared, it is 9 times x plus 1 squared. So it is 9 times x plus 1 squared, x plus 1 squared equals to x squared, plus 1 squared, that is 1, plus 2 times x times 1, that is 2x, and it is equals to 5 times x squared plus 9. So it is 5x squared plus 5 times 9, that is 45. So total we found out that 9 times x squared plus 1 plus 2x equals to 5x squared plus 45. Here we open the brackets of this side of this equation, equation 3, and found out that 9 times x squared is 9x squared, 9 times 1 is 9, 9 times 2x is 18x, and it equals to 5x squared plus 45. Here we subtracted 5x squared for this equation 3, and found out that 9x squared minus 5x squared is 4x squared, and we have plus 18x plus 9, and it equals to 45, because 5x squared minus 4x squared is 0. So in total, we found out that 4x squared plus 18x plus 9 equals to 45. Here we subtracted 45 for this equation, and finally found out that 4x squared plus 18x and 9 minus 45 is minus 36 equals to 0. And then in total, we found out that 4x squared plus 18x minus 36 equals to 0. Here we divided the equation 3 by 4, and finally found out that 4x squared over 4 is x squared, plus 18x over 4 is 4.5x, and the minus 36 over 4 is minus 9 equals to 0 over 4 is 0. So total we found out that according to equation 3, x squared plus 4.5x minus 9 equals to 0. So this is the quadratic equation, and the general formula for a quadratic equation is as follows. Ax squared plus bx plus c equals to 0. This general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. Now a specific quadratic equation, that is to say x squared plus 4.5x minus 9 equals to 0. The variable that you are looking for is x. The coefficient a equals to 1, the coefficient b equals to 4.5, and find the coefficient c equals to minus 9. The only thing that is left to do in order to find out the variable that you are looking for in our specific quadratic equation, that is x is the radius of the semicircle, is just to put the data of our specific quadratic equation in this general formula for x, and this way we'll find out the value of the values of x, that is the radius of the semicircle. Okay, so we did it. We found out that x equals to minus b. B is 4.5, therefore minus b is minus 4.5, and it's equals to minus b, so plus minus square root of b squared. B is 4.5, therefore b squared is 4.5 squared, that is 20.25, minus 4 times a times c. So it is minus 4 times a is also minus 4 times 1 is minus 4 times c is minus 9, so minus 4 times minus 9 is plus 36. So in total, minus 4 times a times c is plus 36. So in total, inside the root, we have 20.25 plus 36 divided by 2a. A is also 2a is 2 times 1, it is 2. So in total, we found out that x equals to minus 4.5 plus minus square root of 20.25 plus 36 equals to 56.25. So inside the root, we left only with 56.25 divided by 2. And the square root of 56.25 is 7.5. So in total, we found out that x equals to minus 4.5 plus minus 7.5 over 2. So here we have two solutions that are possible for x. The first solution for x is as follows. X equals to minus 4.5 minus 7.5 over 2. Minus 4.5 minus 7.5 is minus 12 over 2. Minus 12 over 2 is minus 6. So she found out that the first solution for x is that x equals to minus 6. Actually, x is the radius of the x is the length of this line at ED, and so x is a length, it must be a positive number. Minus 6 is a negative number, so x can be equal to minus 6. X must be a positive number because x is a length. So you can set this first solution for x, and you left only the second solution for x. The second solution for x is as follows. X equals to minus 4.5 plus 7.5 over 2. Minus 4.5 plus 7.5 is 3, so 3 over 2 is 1.5. So the second solution for x is that x equals to 1.5 units in its length. This is the answer that AD is equals to x, and x equals to 1.5 units in its length. Therefore, the base BC of the green tile BEC equals to 1 plus x. X is 1.5, so 1 plus x is 1 plus 1.5, that is 2.5. So the base BC equals to 2.5 units in its length. Our task is to find out the area of this green shape, that is actually the area of this green tile ABC. Again, our task is to find out the area of the green shape, that is the area of the green triangle BEC. The area of the triangle equals to the base of the triangle times the height over 2. We choose the base of the green triangle ABC is the BC times the height edge over 2. Again, the area of the green shape equals to the area of the green triangle ABC. The area of the green triangle ABC equals to the base BC times the height edge over 2. BC is 1 plus x times edge over 2. Again, x is 1.5. Therefore, 1 plus x is 1 plus 1.5, that is 2.5. So the base BC equals to 2.5 times the height edge is 3 over 2. 2.5 times 3 is 7.5. 7.5 over 2 is 3.75, so it's in size. So if you found out that the area that we're looking for this question, that is the area of this green shape, in total it is equal to 3.75 square units in size. So we finish to repeat on the first method, in the next step repeat on the solution of the second method. first of all, ABCD is a rectangle, therefore those four angles are all right angles. We define the length of this right side AD is x, exactly as we did in the first method. So in total, AD equals to 1 plus x. We know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC, but AB is 3, therefore the opposite side DC must be also equal to 3 units in its length. Likewise, according to the sum rule, in the same rectangle ABCD, side AD must be equal to the opposite side BC, but AD in total is 1 plus x, therefore the opposite side BC must be also equal to 1 plus x units in its length. So, first of all, we did the same thing that we already done in the first method. That is to say, we did the construction. From point A, we drew perpendicular on BC. Again, from point A, we drew perpendicular on side BC of this rectangle ABCD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC. This point is point M. By doing this construction, we created quadrilateral AB, ME. Inside quadrilateral AB, ME, we have 1, 2, 3 degrees, and therefore this surface area must be equal to 90 degrees inside, and not, we already done it in the first method, so I'm not do it externally, so I'll do it briefly. So in this quadrilateral AB, ME, we have 1, 2, 3 degrees, and therefore this surface area must be equal to 90 degrees inside, according to the rule that the sum of the areas in a quadrilateral is equal to 180 degrees. So in quadrilateral ABME we have 4 degrees, and therefore quadrilateral ABME is a rectangle. So ABME is a rectangle, but you also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABME, side AB must be equal to the opposite side EM. But AB is 3, therefore the opposite side EM must be also equal to 3 units in its length. We define the length of EM as h, so EM equals to h equals to 3. So we did all the things that we done here in the first method. In the second method, we did another thing. That is to say, we defined angle BEA. This angle is theta. So in the right upper triangle AEB, triangle theta equals to AB over AE. Again, in the right upper triangle ABE, tangent theta equals to AB over AE. AB is 3, AE is 1. So tangent theta equals to 3 over 1, that is 1. So according to equation 1, tangent theta equals to 3. We have the trigonometric identity that says that tangent theta plus 45 degrees equals to 1 plus tangent theta over 1 minus tangent theta. We already found out that tangent theta equals to 3, so we can substitute tangent theta in this equation by 3. We did it. Now we found out that tangent theta equals to 1 plus tangent theta, that is 3, over 1 minus tangent theta. So minus tangent theta is minus 3. So in total, actually found out that tangent theta plus 45 degrees equals to 1 plus 3, that is 4, over 1 minus 3, that is minus 2. 4 minus 2 is minus 2. So in total, actually found out that tangent theta plus 45 degrees equals to minus 2. So according to equation 1, tangent theta equals to 3, and according to equation 2, tangent theta plus 45 degrees equals to minus 2. AD is one side of rectangle ABCD, so AD is a side of a rectangle, it is absolutely a straight line. So if you focus on the right side of this straight line AD at point D, here the sum of the angles must be equal to 180 degrees according to all three. All three said that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have the right side of the straight line AD at point D? We have this angle that is theta, plus this angle that is 45 degrees, plus this third missing angle, total the sum of those three angles must be equal to 180 degrees according to all three. And again, in the right side of the straight line AD, at point D, the sum of the angles must be equal to 180 degrees according to all three. That is to say, theta plus 45 degrees, plus the third missing angle, that is angle DEC, total they must be equal to 180 degrees according to all three. So here we subtract theta plus 45 degrees from this equation, and find out that the missing angle DEC, this is the missing angle DEC, in total it is equal to 180 degrees minus theta plus 45 degrees. Again, this is the missing angle DEC, this is equal in total to 180 degrees minus theta plus 45 degrees. In the next step, we focus on this right triangle, triangle EDC. on the right triangle EDC, on this right triangle EDC, tangents of this angle, this angle 180 degrees minus theta plus 45 degrees equals to DC over ED. Again, tangents 180 degrees minus theta plus 45 degrees equals to DC over ED. In the right lower triangle EDC, tangents 180 degrees minus theta plus 45 degrees equals to DC over ED. DC is 3, ED is X. So total tangent theta equals to 3 over X. So according to equation 3, we have tangent theta of 180 degrees minus 45 degrees equals to 3 over X. Just copy this equation here. Tangent theta minus theta plus 180 degrees minus theta plus 45 degrees equals to 3 over X. We have the trigonometric identity that says that tangent 180 degrees minus theta equals to minus tangent theta. So according to this trigonometric identity, we get the tangent 180 degrees minus theta plus 45 degrees equals to minus tangent theta plus 45 degrees. Okay, so we substitute tangent theta minus tangent 180 degrees minus theta plus 45 degrees by minus tangent theta plus 45 degrees. Those two expressions are equal according to this trigonometric identity. And we have also, it is equal to 3 over X. So I copy it here. For this here, it's equals to 3 over X. So total according to equation 3, we found out that tangent theta plus 45 degrees equals to 3 over X. But we already found out that according to equation 2, tangent theta plus 45 degrees equals to minus 2. Repeat again. According to equation 2, we actually found out that tangent theta plus 45 degrees equals to minus 2. So we have here minus, I copy the minus here, and according to equation 2, tangent theta plus 45 degrees equals to minus 2. So in total, in this side of the equation, we have minus 2 equals to 3 over X. Minus is plus. So minus 2 is plus 2. So 2 equals to 3 over X. Here we multiply this equation by X and found out that 2X equals to 3. Here we divide this equation by 2 and found out that X equals to 3 halves, that is 1.5. X equals to 1.5 units in its length. This is the answer, and ED is equals to X, and X equals to 1.5 units in its length. So the base BC of the green triangle BEC equals to 1 plus X, that is to say it is 1 plus 1.5, that is 2.5. Our task is to find out the area of this green shape. The area of the green shape is actually the area of this green triangle EBC. So our task is to find out the area of the green triangle EBC. The area of the green triangle EBC equals to the base BC times the height edge over 2. Again, the area of the green triangle EBC equals to the base BC times the height edge over 2. BC is X plus 1 times the height edge is 3 over 2. X is 1, so X plus 1 X is 1.5, so X plus 1 is 1.5 plus 1, that is 2.5, so X plus 1 is 2.5 times 3 over 2. 2.5 times 3 is 7.5 over 2. 7.5 over 2 is 3.75 units in 3.75 units in size. So in both methods, we found out that the area that we are looking for in this equation, that is the area of this green shape, is equal to 3.75 units in size. So we finish to repeat on the first question, and the next time repeat on the solution of the second question. The second question, our task is to find out the area of this semicircle. The second question, our task is to find out the radius of this semicircle that is described by this rectangle ABCD. Okay, again, our task is to find out the radius of this semicircle that is described by this rectangle ABCD. Note that this is 9 cm cubic, is equals to 1 unit in its length. This is 9 cm PD, is equals to 2 units in its length. Again, our task is to find out the area and the radius of this circle that is described by this rectangle ABCD. So first of all, quadrilateral ABCD is a rectangle, therefore all of its 4 angles are right angles. No, 4 angles are all right angles. And we know that we define the center of this semicircle, this point is point O. We define the radius of this semicircle as x. The radius of this semicircle equals to x according to our definition. We define the point of tendency of tangent DC with this semicircle, this point is point L. Likewise, we define the point of tendency of tangent BC with this semicircle, this point is point T. In the next step, we join points O and N together by side line. Point O is the center of the circle, point N is the point of the second cell, therefore ON is the radius of this semicircle is equal to x according to our definition. The radius of L is equal to x, the radius of L is drawn to point L, this is the point of tendency of tangent DC with this semicircle. And whenever we have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius LO. If this is perpendicular to LO, it means that this angle equals to 90 degrees in size, and this angle also equals to 90 degrees in size according to Rule 1. In the next step, we join points O and we define we join points O and T together by side line. Point O is the center of the semicircle, point T is the point of the semicircle itself, therefore OT is the radius of the semicircle, this is equals to x. The radius of OT is equals to x, the radius of OT is drawn to point T, this is the point of tendency of tangent BC with this second. Whenever this is drawn to the point of tendency, then tangent BC will be perpendicular to the radius TO. If BC is perpendicular to TO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to Rule 1. So in total, inside the small quadrilateral OTCL, we have 1, 2 furthers. The sum of furthers is 270 degrees. So 270 degrees passes the sides of this fourth angle into that must be equal to 360 degrees. According to the rule that said that the sum of the angles in a quadrilateral is equal to 360 degrees. Therefore, this fourth angle must be equal to 90 degrees inside. So inside quadrilateral OTCL, we have 4 angles, and therefore we can relate to quadrilateral OTCL as right angle. So this is 4 angles. But we also know that the opposite sides of rectangle are equal to each other. So in rectangle OTCL, side OT must be equal to the opposite side LC. But OT is x, therefore the opposite side LC must be also equal to x units in its length. Likewise, according to the sum rule, in the same rectangle OTCL, side OL must be equal to the opposite side TC. But OL is x, therefore the opposite side TC must be also equal to x units in its length. So if you found out that quadrilateral OTCL is not a rectangle but a square, because of the fact that all of its sides are equal to each other, its side equals to x. In the next step, we did the construction, that is to say from point O, that is the center of this semicircle, we do perpendicular on AB. Again, from point O, we do perpendicular on side AB of this rectangle ABCD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O on AB, this point is point Z. By doing this construction, we get the quadrilateral ZBTO. Inside this quadrilateral ZBTO, we have 1, 2 furthers, and therefore this fourth angle must be equal to 90 degrees inside. So quadrilateral ZPTO is 4 angles, and therefore we can relate to quadrilateral ZPTO as a rectangle. But you also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle ZBTO, side OT must be equal to the opposite side ZB. But OT is x, therefore the opposite side ZB must be also equal to x units in its length. What is the ref of this missing side ZQ? ZQ equals to ZB minus QB. ZQ equals to ZB minus QB. That is to say, ZQ equals to ZB, that is x, minus QB, that is 1. So in total, ZQ equals to x minus 1 units in its length. In the next step, we did another construction, that is to say from point O, that is the center of this semicircle, we do perpendicular on AD. Again, from point O, we do perpendicular on side AD of this rectangle ABCD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AD, this point is point K. When doing this construction, we get the quadrilateral AZ, OK. In quadrilateral AZ, OK, we have 1, 2 furthers, and therefore this fourth angle must be equal to 90 degrees inside. So in quadrilateral AZ, OK, we have 4 angles, and therefore we can relate to quadrilateral AZ, OK is a rectangle. By doing this construction, we created another quadrilateral that is the lower quadrilateral KOLD. Inside quadrilateral KOLD, we have 1, 2 furthers, and therefore this fourth piece must be equal to 90 degrees inside. So in quadrilateral KOLD, we have 4 angles, and therefore can relate to this quadrilateral KOLD is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle KOLD, side OL must be equal to the opposite side KD. But OL is x, therefore the opposite side KD must be also equal to x units in itself. What is the length of this missing nice KP? KP equals to KD minus PD. Again, KP equals to KD minus PD. So KP equals to KD, this is x, minus PD, this is 2. So in total, we found out that the missing nice KP equals to x minus 2 units in its length. This is angle, the big angle KOT. The big angle KOT in total equals to 90 degrees plus 90 degrees. 90 degrees plus 90 degrees, it is 180 degrees. So the big angle KOT equals to 180 degrees in its size. And again, the big angle KOT equals to 180 degrees in its size. And we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore, line segment KOT is a straight line. If line segment KOT is a straight line, then line segment KOT is a straight line, then it means that KT is also a straight line. So KT is a straight line. So this is shape AB TK, or shape AB TK is 1, 2, 4, 3 sides. And shape AB TK is 4 sides. Therefore, shape AB TK must be a quadrilateral. Okay. Shape TK AB is a quadrilateral because it has 4 sides. So in quadrilateral ABTK we have 1, 2, 3, 4 right angles. And we have the rule that says that any quadrilateral that has 4 right angles must be at least a right angle if not a square. So we need to do this quadrilateral ABTK is a right angle. But we also know that the opposite sides of a rectangle are parallel to each other. So in rectangle ABTK, side AB must be parallel to the opposite side KT. And again, in rectangle TKAB side and the opposite sides are parallel to each other, that is to say side AB must be parallel to the opposite side TK. The next step we implemented all 10 in our drawing. Those two angles are defined as corresponding angles and are located between the parallel lines AB and TK. Again, we found out that AB is parallel to KT. And because of the fact that those two corresponding angles are located between the parallel lines AB and KT, they must be equal to each other and their sizes according to rule 10. So if you find the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to rule 10. So in the upper right rectangle ZQO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in a triangle. Likewise, in the right ring lower triangle KOP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha according to the sum that says that the sum of the angles in a triangle is equal to 180 degrees. So in the next step, we proved that those two green triangles can go into each other according to angle side angle rule. That is to say, we proved that the upper right green triangle ZOQ, this triangle, it can go into this right lower green triangle KPO according to angle side angle rule. So why those two triangles can go into each other? First of all, those two angles are both equal to alpha and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. And finally, side OQ of this green triangle ZQO is equal to side OP of this green right lower triangle KPO. Therefore, we shall find out that those two right triangles can go into each other according to angle side angle rule. So we shall find out that the upper green triangle ZQO can go into the right lower triangle KPO according to angle side angle rule. That is to say, we shall prove that those two angles and the side that is included between those two angles, that is side OQ, in this upper right triangle ZQO are corresponding equal to those two angles, and the side that is included between those two angles, that is actually side PO, this ring right lower triangle KPO. And therefore, those two right triangles can go into each other according to angle side angle rule. And for the fact that those two right triangles can go into each other, we will derive that their corresponding sides must be also equal to each other at their lengths. According to the rule that says that corresponding sides in congruent triangles are equal to each other. What are the corresponding sides of those congruent triangles? Side ZQ is equal to the corresponding side KO. Why those two sides are corresponding to each other? Because of the fact that both of them are located in front of this angle, the equal to 90 degrees, 1 half. So according to the one that I mentioned, side ZQ equals to side KO. Again, if you found out that according to the rule that corresponding sides can go into equal to each other, side ZQ equals to side KO. But we already found out that ZQ equals to x minus 1, so you can write here that ZQ equals to x minus 1, ZQ equals to x minus 1, and from this equation x minus 1 equals to ZQ equals to KO, we will derive that the missing side KO must be also equal to x minus 1 units in its name. This is the missing side KO, this is also equals to x minus 1 units in its name. We already found out that Kp equals to x minus 2 because of the fact that Kp equals to Kd, that is 2, minus Kd, that is x, minus Pd, that is 2. So Kp equals to x minus 2 units in its name. The next step we present the Pythagoras theorem on this right green triangle OKP. The right triangle KPO or OKP, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, OP squared is the square of the hypotenuse equals to OK square plus KP square. This green triangle KPO, according to the Pythagoras theorem, OP squared, that is the square of the hypotenuse, equals to KO square plus KP square. OP is x, therefore OP square is x squared, it is equal to OK square. OK is x minus 1, therefore OK square is x minus 1 square, plus KP square. KP is x minus 2, therefore KP square is x minus 2 square. So in total, if you found out that x square equals to x minus 1 square plus x plus minus 2 square. You open the brackets on this side of this equation and find out that x square equals to x minus 1 square. X minus 1 square equals to x square plus 1 square, that is 1, minus 2 times x times 1, that is minus 2x, plus x minus 2 square. X minus 2 square equals to x square, plus 2 square, that is 4, minus 2 times x times 2, that is minus 4x. Here we have x square on both sides of this equation, so x square will get cancelled. So after we cancel x square in this side of the equation, we have 3 coming, that is to say 0. While on the other side of the equation, we have 1 plus 4, that is 5, minus 2x minus 4x is minus 6x, plus x square. So total we found out that zero equals to 5 minus x square, plus 0 equals to 5 minus 6x plus x square. So x square minus 6x plus 5 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is as follows: ax square plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula: x equals to minus b plus minus root of b square minus 4 times a times c over 2a. In our specific quadratic equation, that is to say x square minus 6x plus 5 equals to 0, the variable that we are looking for is x. X is the radius of this semicircle. The coefficient a equals to 1, the coefficient b equals to minus 6, and the coefficient c equals to 5. The only thing that is left to do in order to find out the radius of the semicircle that equals to x is just to put the data of our specific quadratic equation inside this general formula for x, and this way we find out the value of the values of x, because x must have 2 solutions. So we did it, and we found out that x equals to minus b. B is minus 6, therefore minus b is minus 6, that is plus 6, plus minus square root of b squared. B is minus 6, therefore b squared is minus 6 squared, that is 36, minus 4 times a times c, so it is minus 4 times a. A is minus 4 times 1 is minus 4 times c. C is 5, so minus 4 times 5 is minus 20. So inside the root we have in total 36 minus 20 over 2a. A is minus 2a, 2 times 1, that is 2. So in total we found out that x equals to 6 plus minus, inside the root we have 36 minus 20 is 16 over 2. So inside the root we have to live with 16. So in total x equals to 6 plus minus, the square root of 16 is 4 over 2. So if you found out that x equals to 6 plus minus 4 over 2. So here we have two solutions that are possible for x. The first solution for x is that x equals to 6 plus 4 over 2. 6 plus 4 is 10 and 10 over 2 is 5. So the first solution for x equals to 5 units in itself. This is to say the radius of this semicircle, x equals to 5 units. We have another solution for x. Another solution for x is as follows. X equals to 6 minus 4 over 2. 6 minus 4 is 2 and 2 over 2 is 1. So the second solution for x is that x, that is the radius of this semicircle, equals to 1 unit in its length. But we already found out that Kp equals to x minus 2. Kp is the length of this transfer. Kp equals to x minus 2 units in its length. Kp equals to x minus 2. So if x equals to 1, then x minus 2 is 1 minus 2. 1 minus 2 is minus 1. So we found out that the length of this Lancet Kp is a negative. It is impossible, but because of the fact that the length must be a positive number. Therefore, x can never be equal to minus 1. The second reason that x can never be equal to minus 1 is because of the fact that Kp equals to x minus 2. Kp is a length, so as a length it must be a positive number. What is a positive number? That is to say it must be greater than 0. So, if this inequality must be greater than 0. X minus 2 greater than 0. Here we add 2 to this inequality and finally found out that x must be greater than 2. If x must be greater than 2, x can never be equal to 1, that is less than 2. So we can have the solution that x equals to 1, x can never be equal to 1. Therefore we have to live with the other solution for x. That is to say the radius x of this semicircle equals to 5 units in its length. Okay, thank you very much.